Woohoo! Welcome back. Today we're going to be working with systems of equations, but this time we're going to be working with 3 equations in 3 unknowns. I know, it's very exciting. Woohoo! And Matt Damon is still here, waiting to hear whether we're going to get him off of Mars or not in his own little spaceship. But first, we got to talk about how we're going to approach 3 equations with 3 unknowns. Unknowns is another word for variable. And so this is called a 3 by 3 system. Now, these are a little more complicated than the 2 by 2 systems we were just working with. So we're going to come up with a few different ways to approach it. And the first one is just to recognize when it's a good situation. And the answer is a good situation is one where you get a system that's in this really interesting form. You'll notice that there are 3 variables in the top equation, which I'm going to call row 1. You can call it something else, but we're setting up for matrices later on. So I'm going to call it row 1. You could also label it anything you'd like, equation 1, whatever. Now, in what I'm going to call row 2, x is missing. There's no x there. It's 0x. And then in row 3, there's 0x and 0y. And that makes a little triangle. Now, to be honest, I'm not sure whether this is the triangle or this is the triangle, but regardless, this is called triangular form. And this makes the world so much easier. If you are lucky enough to stumble upon a 3 by 3 system that's in triangular form, then you can use a fairly simple process called back substitution. What we're going to do is we're going to start at the end and we're going to make our way up. So we're going to go backwards. And we're going to use substitution, which we were just playing with just last video, or a couple of videos ago. So let's talk about what it means. I'm going to start with row 3, and I'll see that z equals 3. Well, we know what z is now. Z is 3, so we're done. Woohoo! If I look at row 2, then I see that y plus 2z equals 5. Well, I know what z is. Z is 3. So I've got y plus 2 times 3 equals 5. Or y plus 6 equals 5. Subtract 6 from both sides. Y equals -1. So I can just plug in the z value there and then do a little subtraction, and I've got the y value. Okay. So then what does row 1 tell us? Well, row 1 says that x minus 2y minus z equals 1. Okay, but I know what y is. Y is -1. And I know what z is. Z is 3. So I get x plus 2 minus 3 equals 1. I combine plus 2 and minus 3. X minus 1 equals 1. And then I add 1 to both sides. So I get x equals 2. So now I fairly quickly ended up with the answer x equals 2, y equals -1, and z equals 3. Now, this is no longer an ordered pair because there's not a pair. There are 3 of them. So this is called an ordered triplet. Sorry about that. Or an ordered, oh my goodness, this is causing me so much trouble. An ordered triplet or an ordered triple. I've got it written right here. You don't have to listen to me. It's written down. So the ordered triple is basically an ordered pair, just a little bit longer. So you do the 2, the -1, and the 3. So you list x and y and z. And now we're in 3 dimensions instead of 2, which is pretty cool. So this is going to be the standard for how we're going to solve 3 by 3 systems. And because this works so well, basically this is the goal right there. whatever you need, whatever you do, make that triangle of zeros. So here are the steps. Now, the next page can be a little intimidating. There's a lot of rules, there's a lot of words, and I'm going to remind you that most of math is not something you read, it's something you do, it's something you practice. So I will go over what the instructions are, and then we will actually practice a couple of these. So let's go ahead and get started. Okay, you ready? Dun dun dun! So this is known as Gaussian elimination, and named after Gauss. And there are certain rules that are going to seem kind of familiar if you've been working with the 2x2 systems, 2x2 in 5.1. So if you come across a 3x3 or larger, and we're going to leave that open, that's going to be for a later time, system of equations that's not in triangular form, then we use an expanded version of elimination. So we're building on elimination, and it's called Gaussian elimination. So what are the rules? You are allowed to add a non-zero multiple. So it means multiply one of the equations by a number that's not zero, and then add it to another equation. You're allowed to multiply an equation by a non-zero constant. Again, don't multiply by zero because everything disappears. And you're allowed to interchange the positions of two equations. So here's a big note. There may be multiple ways to solve any given system, so don't worry about not following the examples exactly. The goal is usually to eliminate a variable in each step and come up with an equivalent triangular system if possible. But sometimes it can take a few extra steps to get everything to line up properly. There are so many different ways to approach this. And I mean, technically, there are an infinite number of ways to solve each of these systems. Realistically, there's maybe a half a dozen different ways that will all lead you to the same result. So again, if you go a different path, just make sure you're following these rules and follow the practice. And then always, if you have questions, ask. You can always ask a tutor. You can ask me, say, am I doing okay? Is this good? What could I be doing differently? How can I refine my process? There aren't really any bad choices. There are just choices that will lead you to situations where it's going to take a lot longer to solve the problems. So, okay, here we go. Let us solve this system. Here we go. Woohoo. I've got, again, I'm going to call this row 1, I'm going to call this row 2, and I'm going to call this row 3. And I'm going to use these because I personally think it's a really good idea to identify which of the equations were, what we did with each of the various equations, if that makes any sense. So I'm going to go ahead and I'm going to take a look here and see that I've got an x by itself in that first row. I've got 2 x's down here and 3 x's down here, and I'm going to try to get them right. Here's my zeros that I'm looking for. It might not turn out that way, but that's what I'm going to aim for. So what I'm going to do is I'm going to take row 2 and subtract 2 times row 1 and put that back in row 2. And if you've never seen this kind of notation, it's going to be a lot. So let me show you what this means. So here's row 2, 2x plus 2y minus z equals 6, and 2 row 1, okay, that's going to be 2x plus 4y minus 4z equals 2. So this is 2 times row 1. And now here's the thing. I can't really subtract. So this is going to depend on how much you want to follow the spirit of the law in math. So technically speaking, you can only officially add. So if I want to subtract, I have to multiply by a -2. So that makes this a -2x, a -4y, a +4z, and a -2. If you're not going to worry about that, which I totally understand, then you can consider it subtraction. So I'm going to leave it up to you. We're adding the opposite. Now, when we add, the x's disappear. They cancel out. Then I get -2y plus 3z equals 4. And then I'm going to rewrite, I'm going to rewrite the system. The system is now x plus 2y minus 2z equals 1. That's row 1. Same row 1. Row 1 did not change. 3x plus 4y minus 3z equals 5. That's row 3. And then this new version, this new R2, my new row 2, is going to go right here. -2y plus 3z equals 4. That's my new row 2. And this is what we're going to do. We're just going to keep, so I'm going to use this x. I use this x to get rid of the 2x in the middle. It's gone now. I'm going to use this x to get rid of that 3x. And I'm just going to keep going like this. Okay, so I believe, do I have some space? Yes, I do. So my next step is going to be that I'm going to take row 3 and I'm going to subtract, or I'm going to add the opposite of row 3 times row 1 and put that back in row 3. So row 3 is 3x plus 4y minus 3z equals 5. That's this guy down there. And then I want -3 times row 1. Okay, so row 1 is this one. So I have x. I'm going to get -3x. -3 times 2y is -6y. -3 times -2z is plus 6z. And -3 times 1 is -3. And then I'm going to add it all together. So now I'm going to get that 0 in the first position that I'm looking for, minus 2y, let's see, plus 3z equals 2. And then I'm going to put that, that's going to be the new row 3. So now let's write down the system. I've got x plus 2y minus 2z equals 1. That's the old row 1. I've got -2y plus 3z equals 4. That's row 2. And then I've got my new row 3, which is going to be 0 minus 2y plus 3z equals 2. That's my row 3. And I'm going to keep going like this. I'm going to keep trying to eliminate. So I got a 0 there, a 0 there, so I want to get a 0 here. So I'm going to use this -2y to get rid of that -2y. Now they match up. So previously I had to multiply by a number to get the x's to match up. The y's already match up. I just have to, what do I have to do to get them to add? And the answer is I have to change the sign. Okay, so I'm going to take row 3 minus row 2 and put that in row 3. Now, technically speaking, this is the way I was told to write it. But of course, what we're talking about is we're doing plus the opposite, right? So we're talking about something slightly different. But let's see, I've got -2y plus 3z equals 2. That's row 2. or sorry, that's row 3. And then the opposite of row 2 is going to be 2y minus 3z equals -4. And let's see what happens when I add. I get a 0 here, I get a 0 here, and then I get -2. So now I have 0 equals -2, and this is my new row 3. Now, normally we would just keep going. We just keep going, keep doing this, and keep eliminating terms. Except I've got a problem. It's a great problem to have, actually. If you're tired of this problem, you're done with this problem because of this problem. This is false. Notice how all the variables dropped out. I don't have a y or a z left over. If all the variables are gone, you got a 0 on the left and a number on the right. This is false, which means that this system of equations, they don't work together. So all 3 of these equations don't have a single solution that works for all of them. So as soon as we get to a false statement like this, we stop. We say this is false, it's inconsistent. There's no solution. So you know what that means. You got it. Very sad, Matt Damon. I'm sorry, Matt Damon. No spaceship today. Oh, very sad, very sad. Okay. So, but happy for us because why? Well, we don't have to keep going. So what is the takeaway? Are we hoping for inconsistent systems? And the answer is no, we're not hoping for that. What we're hoping for is we're hoping that we're able to get to the point where we can eliminate these 3 variables. This x, and this y. We can get rid of these 3 terms, and then we can do this process to get a solution so that this, I mean, I feel like we can come back here and do a little dance party. This is happy Matt Damon. Yay. So this is Matt Damon gets to go home. This is Matt Damon is going to be stuck on Mars for just a little bit longer until we can set up a different system for his spaceship. So, okay. That was exciting. I've got one more example I want to do for you. And then I want to make a promise, and that is that by the time you start doing some of this homework, you're going to be so done with variables, and you're going to say to yourself, oh my goodness, I'm so tired of variables. I don't want to do this anymore. And do I have a deal for you? In the very next chapter we're going to get rid of all the variables. It will just be the numbers. It'll be so much simpler. So hold out for that. Do the practice. Give yourself a little bit of a break. Get a snack, something nice to drink. You know, take a break and, you know, pet an animal, pet a cat, or, you know, draw pictures or sing a song or whatever it is you do to take a break, and then come on back and we will math on.